Right now, as you are watching this, an object from another star system is passing behind our Sun, and here is what makes your spine tingle. NASA has the data. The James Webb Space Telescope captured something in August 2025 that breaks every model we have for how comets should behave. The implications are buried so deep in technical language that most people will never understand what they're actually looking at. How is that even possible in an age where we're supposedly committed to open science and public transparency? Let me give you one number, just one. The carbon dioxide to water ratio detected in 3I Atlas's coma, 8:1, the highest ever recorded. Not just unusual, not just surprising, the highest in the history of comet observation. And when NASA released these findings, they wrapped them in carefully worded press releases, academic papers with jargon that would make your eyes glaze over, and public statements that essentially said, "It is just a comet, move along." But here is what they're not emphasizing. That ratio doesn't fit any formation model we have for objects in our solar system. It suggests something about where this object came from, how it formed, and what it is made of that challenges our fundamental understanding of planetary system chemistry. This isn't about conspiracy theories or wild speculation. This is about reading between the lines of what NASA's own scientists are publishing in peer-reviewed journals versus what is being communicated to you and me, the people who fund these missions through our tax dollars. There is a gap, a significant one. And that gap exists because what the data actually suggests doesn't fit the comfortable narrative that the public has been fed since October 2024, when this thing was first spotted. If you want to know what NASA's scientists are really thinking behind closed doors about 3I Atlas, if you want to understand why certain researchers are using terms like major anomaly and black swan event, you need to stay until the end of this video, because what we're going to uncover together isn't just about one interstellar visitor. It is about how information gets filtered, sanitized, and packaged between the scientists who discover it and the public who has every right to understand it. But first, do me a favor. Hit that like button right now and drop a comment telling me where you are watching from. Because what we're about to dig into isn't just an American story or a NASA story. This is about how space agencies worldwide handle discoveries that don't fit neatly into existing frameworks. Let's pull back the curtain and see what is really going on with 3I Atlas. Chapter 1. The JWST Bombshell, Extreme Carbon Dioxide Dominance on August 6, 2025. The James Webb Space Telescope JWST pointed its instruments at 3I Atlas. This wasn't a casual observation. JWST doesn't waste time. Every second of its observation schedule is planned months in advance, allocated to projects that compete fiercely for telescope time. The fact that JWST was directed to observe an interstellar comet tells you something right there. Scientists wanted detailed spectroscopic data, and they wanted it badly enough to justify using humanity's most advanced space telescope. What came back from that observation session changed the conversation entirely. The near-infrared spectrograph detected a coma, that hazy cloud of gas and dust surrounding a comet's nucleus, that was absolutely dominated by carbon dioxide. When I say dominated, I mean that the carbon dioxide to water ratio was 8:1. For every molecule of water vapor JWST detected, there were 8 molecules of carbon dioxide. Let me put that in perspective for you. The typical comet we observe from the Oort cloud or the Kuiper belt shows the opposite ratio. Water is usually the dominant volatile, the primary substance that sublimates off the surface as a comet approaches the sun. Carbon dioxide is present, sure, but as a secondary component. An 8:1 ratio flips that script entirely. NASA's press release mentioned this finding. They published the data in the Astrophysical Journal. The numbers are there for anyone to read. But here is where the communication gap opens up. Those press releases didn't spend time explaining what this ratio actually means. They didn't walk the public through the implications, because when you understand what creates a carbon dioxide-dominated coma, you start asking uncomfortable questions about where 3I Atlas came from and how it formed. There are only 2 hypotheses that NASA scientists have put forward to explain this composition, and here is the thing that should bother you. The press releases present these as equally plausible when the evidence may actually favor one over the other. Hypothesis 1. 3I Atlas formed in a protoplanetary disk, in an unusual region, perhaps far from its parent star, where temperatures were cold enough that carbon dioxide ice condensed more readily than water ice. This would require specific conditions that aren't common, but they're theoretically possible. Hypothesis 2. This object formed in a more typical region, but it was exposed to extreme radiation from its host star or nearby stellar companions that selectively removed water ice from its surface. leaving behind a carbon dioxide-rich shell. Both explanations require special circumstances. Neither suggests this is a typical comet. And that is the point NASA isn't emphasizing. Whether it's explanation 1 or explanation 2, you are looking at an object that didn't form under normal conditions. It is an outlier, an anomaly. And when you start combining this with the other data we have, the anomalies start stacking up in ways that make you wonder what else isn't being clearly communicated. Chapter 2. Stacking anomalies, ice structure, and distant activity. The James Webb Space Telescope data revealed more than just gas composition. The water ice grains detected in the coma were smaller than 1 micrometer. That is incredibly fine, like powder. And there is evidence suggesting the ice structure might be amorphous rather than crystalline. What does that mean? It means this ice never underwent the kind of thermal processing that most solar system comets experience. Amorphous ice forms at extremely low temperatures and stays amorphous unless it is heated. If 3I Atlas retained amorphous ice, it suggests it spent its entire existence in a cold environment, never coming close enough to a star to trigger the phase transition to crystalline structure. That is consistent with an object that formed in the outer reaches of another star system and was ejected into interstellar space billions of years ago. But then there is the Swift Observatory detection from mid-2025, and this is where things get interesting in a way that doesn't quite fit the narrative. Swift detected what appeared to be water sublimation happening between 4,000 and 10,000 kilometers from the nucleus. That is far, really far. For context, most comet activity happens much closer to the nucleus within a few hundred kilometers. Water doesn't typically sublimate at those distances unless something unusual is going on with the grain size distribution, the particle velocities, or the way sunlight is being absorbed and radiated. NASA's reports mention this observation, but don't dwell on why it is strange. They file it under interesting finding and move on. Here is what you need to understand. Every single one of these data points taken individually can be explained. Scientists are good at that. Give them an anomalous reading and they'll construct a model that accounts for it. But when you start stacking these data points together, when you look at the whole picture, you are not looking at a comet that is slightly unusual. You are looking at an object that deviates from the norm in multiple independent ways. And that pattern of deviation is what should make you sit up and pay attention. The August data also gave us emission rates. 3I Atlas was releasing approximately 129 kilograms of carbon dioxide per SE cond. Compare that to 6.6 kilograms of water per SE cond. That is not a small difference. That is a fundamental imbalance in outgassing composition, and it raises an immediate question. If this object is releasing gas at these rates, where is the corresponding acceleration? Because when a comet releases gas, those jets create thrust. They act like tiny rocket engines pushing the nucleus in different directions. It is called non-gravitational acceleration, and every active comet shows it, except apparently 3I Atlas. We're going to come back to that in a moment, but keep it in your mind. Gas emission without expected acceleration. That is problem number 1 that doesn't have a clean answer. NASA released this data, they published it, they made it available. But the framing, the context, the emphasis on how these findings fit together was carefully managed. Technical accuracy without interpretive transparency. That is the gap I'm talking about. You can't accuse them of lying because the data is right there in the journals, but you can absolutely question whether the public communication gives people the tools to understand what they're actually seeing. And when the implications are this significant, when you are talking about an interstellar object that doesn't behave like anything we've seen before, that gap matters. So ask yourself, if you only read NASA's public statements, would you walk away thinking 3I Atlas is just a mildly interesting comet? Or would you understand that its chemical composition represents a genuine puzzle that challenges our models? The answer to that question tells you everything about how information flows from discovery to public awareness. Chapter 3. Unfamiliar chemistry, metals, organics, and rapid evolution. Let's go deeper into what we're actually seeing in the spectroscopic data, because the carbon dioxide ratio is just the beginning. On September 12, 2025, the Spectropolarimetric High Contrast Exoplanet Research Instrument, SPHERE for short, conducted extended observations of 3I Atlas and detected an enormous carbon dioxide coma, stretching more than 348,000 kilometers across. To give you a sense of scale, that is almost the distance from Earth to the Moon. This object is dragging a massive cloud of carbon dioxide as it moves through the inner solar system. That is not normal. Even for carbon dioxide-rich comets in our solar system, we don't see comas that extended and that dense. But it gets stranger. The Very Large Telescope VLT in Chile turned its instruments toward 3I Atlas in late August and detected cyanide gas. Not just trace amounts, measurable quantities of CN radicals in the coma. Cyanide in comets isn't unheard of, but it is also not standard. It indicates the presence of organic compounds, carbon-nitrogen bonds that form under specific conditions. And then there is the atomic nickel vapor. Yes, nickel. The VLT detected emission lines consistent with nickel atoms in the gas surrounding this object's nucleus. Now, let me explain why nickel vapor should make you raise an eyebrow. Nickel is a metal. It has got a high vaporization temperature. For nickel to be present as a gas in a comet's coma, the nucleus has to contain nickel-bearing minerals, and those minerals have to be heated enough by sunlight to release nickel atoms into the surrounding space. We've seen this in a handful of solar system comets, but it is rare. It suggests that 3I Atlas's nucleus isn't just ice and rock. There is a metallic component, possibly from the core of a differentiated body that broke apart or from metal-rich grains that accreted during formation. Either way, it is adding another layer to the composition profile that doesn't match the standard model of an icy comet from the outer regions of a planetary system. Then we get to the James Clerk Maxwell Telescope, JCMT data from early September 2025. And this is where the timeline compression becomes really interesting. Between September 7th and September 14th, JCMT measured the hydrogen cyanide production rate from 3I Atlas. Over the course of just 1 week, that production rate tripled in 7 days. That kind of rapid increase in outgassing activity suggests the nucleus was undergoing significant changes as it approached the Sun. Maybe fresh ice was being exposed as surface layers sublimated away. Maybe thermal stress was fracturing the structure, opening up new vents. But whatever the mechanism, the rapidity of the change indicates an object that is responding to solar heating in dynamic, perhaps unstable ways. Here is where the conversation in the scientific community gets quietly uncomfortable. If you read the academic literature, if you go into the preprint servers where researchers post preliminary findings before peer review, you'll find papers that note this chemical profile doesn't match typical Oort cloud objects. It doesn't match Kuiper belt objects. It doesn't cleanly match the other interstellar comet we've studied in detail, Borisov. Borisov showed a much more water-dominated composition, its gas production rates, its dust, gas ratio, its overall behavior was far more consistent with what we expect from solar system comets. Borisov was weird because it came from another star, but its chemistry was familiar. 3I Atlas is weird because it came from another star and its chemistry is unfamiliar. Some researchers, and I am being careful with my language here because this is still a minority position, have started asking whether 3I Atlas formed in the same kind of environment that produced Borisov. What if different planetary systems produce different populations of comets depending on the star's mass, its metallicity, the architecture of the planetary system? What if 3I Atlas came from a system that was fundamentally different from whatever system ejected Borisov? That is a reasonable scientific question. It is the kind of thing you'd expect researchers to explore, but it also means we can't just assume all interstellar comets will look like the comets we're used to. And that assumption, that unspoken expectation that interstellar visitors will be chemically similar to our own icy bodies, might be coloring how findings are communicated to the public. Let's talk numbers again, because numbers don't lie. In August 2025, when 3I Atlas was still relatively far from the Sun, it was producing 129 kilograms of carbon dioxide per second and 6.6 kilograms of water per second. By mid-September, as it got closer, those rates increased. The hydrogen cyanide rate, as I mentioned, tripled in a week. But here is the thing that should bother you. Despite this substantial gas emission, despite the fact that this object is actively shedding mass and releasing volatiles, there is minimal evidence of the non-gravitational acceleration you'd expect to see. We're going to dive deep into that in the next section, but I am bringing it up now because it connects to composition. If the outgassing is predominantly carbon dioxide, and if that outgassing is somehow symmetrical around the nucleus, you might not see directional acceleration. But achieving that kind of symmetry is really hard. Comet nuclei are irregular potato-shaped objects with uneven surface compositions. They rotate, they have active regions and dormant regions. Getting perfectly balanced outgassing from such an object is almost impossible, unless the nucleus is much larger and more massive than we think, which dampens the effect of the jets, or unless something else is going on that we don't understand. The nickel vapor detection adds weight to the hypothesis that this nucleus might be larger and more substantial than initial estimates suggested. if there is a significant metallic component, if the nucleus contains materials that survive differentiation in a parent body, you are potentially looking at a denser, more massive object than a typical ice and dust comet. And mass matters because it directly affects how much acceleration you get from a given amount of thrust. A small, low-mass comet gets pushed around easily by outgassing jets. A large, high-mass object barely budges. NASA's public communications mention these spectroscopic findings. They acknowledge the detections, but they don't connect the dots in a way that makes the strangeness obvious. They present each finding as an isolated data point. We detected carbon dioxide. We detected cyanide. We detected nickel. What they don't say clearly is these detections together paint a picture of an object that doesn't fit our existing models, and we're not entirely sure how to explain it. That second statement is accurate. It is honest. It is what the science actually shows, but it is not what you'll find in the press releases. And that brings us to the question you should be asking yourself. Why is there a consistent pattern of underemphasizing the strangeness? Is it because NASA doesn't want to fuel speculation? Is it because they're waiting for more data before making stronger statements? Is it because the public communication strategy is designed to avoid panic or confusion? All of those might be true, but they don't change the fact that if you are only consuming the official public-facing statements, you are getting a sanitized version of a much more complex and puzzling reality. And in the age of information, when we have access to the academic papers, when independent researchers can analyze the same data, that sanitization becomes obvious. It becomes a choice. And choices about what to emphasize and what to downplay reveal priorities. So what are NASA's priorities when it comes to 3I Atlas? That is the question we need to keep asking as we go deeper. Chapter 4, the acceleration paradox. Now we get to the physics problem that is keeping orbital dynamicists up at night. When a comet releases gas, the jets create thrust. This is basic rocket science. The gas molecules shoot out from the surface at high velocities, and by Newton's third law, the nucleus experiences an equal and opposite force. Over time, these forces accumulate and create what we call non-gravitational acceleration. It is not much, but it is measurable, and it is a signature feature of every active comet we've ever tracked. The acceleration affects the orbit, causing the comet to arrive at perihelion slightly earlier or later than gravitational calculations alone would predict. We can measure these deviations with high precision, and we use them to constrain models of the nucleus's rotation, its active regions, and its mass. 3 Atlas is releasing gas. We know this from direct spectroscopic observation, 129 kilograms of carbon dioxide per second in August, with increasing production rates as it approached the Sun. That is not a trivial amount. For comparison, some of the most active periodic comets in our solar system release similar amounts of material, and yet the orbital tracking data for 3I Atlas shows minimal to no non-gravitational acceleration. The object is following a trajectory that is almost perfectly explained by gravity alone. How is that possible? There are two main explanations and neither one is comfortable. Explanation 1, the nucleus is far larger and more massive than the initial estimate suggested. If the nucleus is 5 kilometers across or more, if it is tens of billions of tons in mass, then the thrust from outgassing becomes negligible compared to the object's inertia. It is like trying to push a freight train with a handheld fan. The jets are there, they're producing thrust, but the object is so massive that the acceleration is below our detection threshold. This explanation works mathematically, but it creates a new problem. An interstellar comet with a 5-kilometer nucleus is extremely rare. Objects that large are hard to eject from planetary systems. They're more gravitationally bound. The fact that we detect one in the small sample size of 3 confirmed interstellar objects would be statistically surprising. Explanation 2. The outgassing is almost perfectly symmetrical. If jets are firing from all over the surface in a balanced way, the thrust vectors cancel out and you get no net acceleration. This is theoretically possible, but it requires a very specific set of conditions. The nucleus would need to be unusually spherical, or its rotation would need to be aligned in just the right way, or the surface composition would need to be remarkably uniform. None of those characteristics are typical for comets. In fact, most comets are wildly asymmetrical, both in shape and composition. Getting balanced outgassing from such objects is the exception, not the rule. Chapter 5, Controversy and Trajectory. The artificial hypothesis here is where things get controversial, and I need to be clear about what I am presenting. In September 2025, A.V. Loeb, the Harvard astronomer who has become well known for his hypothesis about interstellar objects potentially being artificial, published comments calling the lack of non-gravitational acceleration a major anomaly. His argument goes like this. If you have significant outgassing with no corresponding acceleration, and if the explanations for that require either statistical improbability or very specific geometric configurations, then you should at least consider alternative hypotheses. Loeb suggested, and I am quoting here, that this acceleration pattern could be consistent with an object that is using its outgassing for controlled propulsion rather than random venting. In other words, a spacecraft using its volatiles as reaction mass in a directed way. Now, before you jump to conclusions, let me be very clear. Loeb's position is not the mainstream scientific consensus. The vast majority of astronomers studying 3I Atlas believe it is a natural object, an interstellar comet with unusual but ultimately explainable properties. Loeb himself acknowledges that his hypothesis is speculative and that more data is needed. But here is why I am mentioning it. Loeb's hypothesis is testable. It makes predictions. If 3I Atlas were artificial, if it were attempting to break and enter orbit around the Sun, you'd expect to see specific trajectory modifications as it rounds perihelion. You'd expect the object to maintain activity levels that are consistent with controlled burns rather than thermally driven sublimation. These predictions can be checked against observational data, and that is how science should work. You propose a hypothesis, even a controversial one, and you test it. The problem is that NASA's public communications don't engage with this at all. They don't address Loeb's suggestions. They don't explain why the mainstream view is more plausible. They simply ignore the controversy, which has the effect of making people more suspicious, not less. If the data clearly supports natural explanations, why not say that explicitly? Why not put out a statement that says, "We're aware of speculative hypotheses about artificial origins, and here is why our data doesn't support them"? That kind of transparency would actually build trust. The silence does the opposite. Let's talk about the orbit itself. Because the trajectory of 3I Atlas is remarkable in ways that go beyond the acceleration question. The orbital eccentricity is 6.2. That is hyperbolic. It means this object is on an unbound trajectory. It came into the solar system from interstellar space, and it is going to leave again, heading back out into the void. Its incoming velocity relative to the Sun was 58 kilometers per second. That is fast, but it is not the fastest interstellar object we've seen. Oumuamua was moving faster. What makes 3I Atlas unusual is the orbital plane alignment. The object's orbit is tilted only 5 degrees from the ecliptic, the plane in which the planets orbit the Sun, and it is retrograde, meaning it is moving in the opposite direction to the planets. That combination, low inclination plus retrograde motion, is statistically unusual. If interstellar objects arrive from random directions, you'd expect their orbital planes to be randomly distributed too. Some would be tilted at high angles, some at low angles, some prograde, some retrograde. The fact that 3I Atlas came in nearly aligned with the ecliptic, but moving backward is depending on whose statistical model you use. A several percent level coincidence. Not impossible, not even particularly rare if you are looking at large sample sizes, but noticeable enough that it has been remarked upon in the academic literature. Some researchers have calculated that the probability of 3I Atlas's trajectory, including close approaches to Venus, Mars, and Jupiter, combined with its ecliptic alignment and perihelion timing, is somewhere around 0.005%. That is 1 in 20,000. Those are lottery ticket odds. And again, to be very clear, low probability events happen all the time. Someone wins the lottery every week. But when you are looking at an object that is already anomalous in multiple other ways, and then you add a statistically improbable trajectory, it is worth asking, are we looking at a cluster of coincidences? Or is there something we're missing about how this object moves? The mass estimate is directly tied to the acceleration question. If 3I Atlas is small, under 1 kilometer in diameter, its mass would be in the hundreds of millions of tons. An object that size releasing the amount of gas we observe should show measurable non-gravitational acceleration. It doesn't. So either the mass estimate is wrong, which means the object is much larger, or the outgassing geometry is extraordinarily balanced. NASA's Hubble observations suggest a diameter range between 0.32 and 5.6 kilometers. That is a huge range. It exists because we can't separate the light from the nucleus from the light scattered by the coma. When you look at 3I Atlas through a telescope, you see a fuzzy blob. You can't resolve the solid nucleus at the center, so you have to infer its size from brightness and assumptions about reflectivity. And that gives you a very wide margin of error. If the true diameter is closer to 5 or 6 kilometers, you are looking at a mass in the range of 33 billion tons or more. Assuming typical comet density, that is massive. That is large enough that the outgassing thrust becomes a small perturbation rather than a significant force. But it also means you are looking at one of the largest interstellar objects ever detected, and you have to ask, how did something that big get ejected from its home system? Typically, smaller objects get kicked out more easily during planetary migrations or stellar encounters. Large objects stay bound, so if 3I Atlas is large, its presence here is itself a puzzle. This is the kind of nuance that gets lost in press releases that say interstellar comet passes through solar system. Technically true, completely uninformative about the actual science. And that gap, that space between what is technically accurate and what is meaningfully transparent, is where distrust grows. Because people aren't stupid. They can sense when they're being given the sanitized version. They might not have the technical background to articulate exactly what is missing, but they feel it. And that feeling drives them to seek alternative explanations, alternative sources of information, some of which are responsible and some of which are not. NASA could short-circuit that entire process by being more forthcoming about the genuine puzzles in the data, but they're not. And that is a choice. Chapter 6. The Mars Flyby and the Information Void. On October 13, 2025, 3I Atlas made its closest approach to Mars, passing within 0.19 astronomical units of the planet. That is about 28 million kilometers, which sounds like a lot, but in astronomical terms, it is close enough that spacecraft orbiting Mars had an opportunity to observe. The European Space Agency's ExoMars Trace Gas Orbiter, JWST, did exactly that. Using its color and stereo surface imaging system, CASIS for short, the orbiter captured images of 3I Atlas during the flyby. This was not a trivial observation. CASIS is designed to image the Martian surface at high resolution. It is optimized for bright targets in reflected sunlight. 3I Atlas, even at closest approach, was 50,000 times fainter than the surface features CASIS normally photographs. To image something that dim, the instrument team had to use 5-second exposures, which is long for a spacecraft-mounted camera. Longer exposures mean you are more vulnerable to motion blur, to scattered light contamination, to any vibrations in the spacecraft. The fact that they attempted it at all tells you the scientific community wanted that data badly. What did CASIS capture? Coma imaging. The extended gas clouds surrounding the nucleus. The images confirmed the coma's extent, its overall morphology, and provided context for the spectroscopic data being gathered by ground-based telescopes. What CASIS did not capture was a resolved image of the nucleus itself. The nucleus remained unresolved, a point source buried in the glow of the coma. This is the same problem Hubble had. You can see the cloud, but you can't see the solid body at the center with enough clarity to measure its size directly. So, the mass ambiguity remains. Now, here is where the communication gets muddy. In late October 2025, reports began circulating on astronomy forums and social media claiming that NASA's Perseverance rover on the Martian surface had also captured images of 3I Atlas during the close approach. Some of these reports included what appeared to be screenshots or image excerpts. The problem: NASA never officially confirmed those observations. There has been no press release from the Perseverance mission team. There has been no publication in the scientific literature. The images, if they exist, haven't been released through official channels. This is the kind of ambiguity that drives people crazy. Either Perseverance imaged it or it didn't. If it did, where are the images? If it didn't, why are there reports claiming it did? The most likely explanation is that someone either misidentified images from another source or created mock-ups based on speculation, and those false images spread faster than corrections could catch up. This is the internet in 2025. Misinformation moves at light speed. But here is the thing that makes NASA's silence on this frustrating. A simple statement clarifying whether Perseverance observed 3I Atlas would end the speculation immediately. Put out a tweet, update the mission page, say yes or no. The fact that there has been no clarification allows the ambiguity to fester, and ambiguity breeds conspiracy thinking. What we do know for certain is that ExoMars TGO made the observation, that the data exists, and that it is being analyzed. ESA released preliminary information confirming the observation, but detailed analysis hasn't been published yet. That is normal in science. Data takes time to process, to calibrate, to interpret. But the delay between data acquisition and public release creates a window where speculation fills the void. And in that void, people start asking, what did they see that they're not telling us? Even if the answer is nothing unusual, just what we expected. The lack of timely communication makes it seem like something's being hidden. Then there is the JWST weather satellite. This is an interesting piece of the puzzle that most people don't know about. JWST is a US geostationary weather satellite positioned over the Western Hemisphere. Its primary job is monitoring Earth's weather, but it has cameras that can see beyond Earth. And during the solar conjunction period, when 3I Atlas was passing behind the Sun from Earth's perspective, JWST had a viewing angle that kept the object outside the Sun's glare. Reports emerged suggesting JWST captured imagery of 3I Atlas during this period, October 21st through late October 2025, when Earth-based telescopes couldn't observe due to solar interference. Again, no official confirmation from NOAA, the agency that operates JWST. No images released, just unverified reports in the amateur astronomy community. And again, the pattern is the same. Potential observation that would be scientifically valuable, claims that it happened, no official acknowledgement. Why? If JWST captured images, even low-resolution ones, they'd add to the timeline of observations during a critical period when the object was closest to the Sun. If JWST didn't capture images, or if the images were too poor quality to be useful, say that. The silence is what creates suspicion. Let me be fair to NASA and ESA for a moment. Space agencies are bureaucratic institutions. They have protocols for data release. They have peer review processes. They have public affairs offices that coordinate messaging. All of that takes time. And in the meantime, the scientific community is working on the data, writing papers, checking results. What looks like delay or silence from the outside might just be the normal grinding of institutional gears, but perception matters. And the perception right now in the astronomy community and among the interested public is that information about 3I Atlas is being released slowly, selectively, and without adequate context. The Mars flyby represents a missed opportunity for high-resolution imaging. If Perseverance had been tasked to observe, if its cameras had been pointed skyward instead of at rocks, we might have resolved the nucleus. We might have answered the size question definitively. But rover operations are planned in advance. And retasking for a target of opportunity, like 3I Atlas, requires flexibility that doesn't always exist in mission operations. So, we're left with what we have: ExoMars coma images that confirm activity, but don't resolve the nucleus, and a cloud of unverified claims about other observations that may or may not exist. What bothers me about this entire situation is how easily it could have been avoided. NASA knows that 3I Atlas is generating public interest. They know that speculation is running wild on social media. A single comprehensive briefing where they lay out what has been observed, what hasn't, what the data shows, and what remains unknown would cut through the noise. Instead, we get piecemeal releases, journal papers that take months to publish, and silence on the rumors. That is a recipe for distrust. And in an era where scientific institutions are already facing credibility challenges, where public trust in expertise is fragile, this communication strategy seems almost willfully counterproductive. The fact that we're now in late October 2025, that perihelion has just occurred, and that we still don't have a clear public statement on what the Mars orbiters and other platforms observed tells you everything about the gap between data acquisition and public transparency. The data exists. It is sitting on servers at ESA, at NASA, in university research groups. Scientists are analyzing it. Papers are being written, but for you and me, for the people who want to understand what is happening with this interstellar visitor, we're left piecing together fragments from press releases, preprint servers, and forum posts. That shouldn't be how this works. Chapter 7, The Black Swan Problem, Size Uncertainty, and its cost. The size of 3I Atlas's nucleus is, without exaggeration, one of the most important unknowns in this entire story. And the fact that we still don't have a firm answer 6 months after detailed observations began should tell you something about the challenges of studying interstellar objects. When Hubble pointed its instruments at 3I Atlas in mid-2025, astronomers were hoping to get a direct measurement of the nucleus diameter. What they got instead was a range somewhere between 0.32 kilometers and 5.6 kilometers across. That is not a small margin of error. That is a 17-fold uncertainty. It is the difference between a modest icy boulder and a small mountain. Why such a huge range? Because when you look at 3I Atlas through a telescope, you don't see the nucleus, you see the coma. The nucleus is buried inside that cloud of gas and dust, and separating the faint light reflected off the solid body from the much brighter light scattered by the surrounding material is incredibly difficult. Astronomers use models to subtract the coma's contribution, but those models depend on assumptions about the dust size distribution, the gas production rate, and the scattering properties of the particles. Change those assumptions and your derived nuclear size changes dramatically. If 3I Atlas is on the small end of that range, around 0.5 kilometers in diameter, it fits within the expected population of interstellar comets. Planetary formation models predict that billions of comet-sized bodies get ejected from young star systems during the chaotic early phases when giant planets migrate and gravitationally scatter smaller objects. A half-kilometer comet finding its way to our solar system is statistically reasonable. It is not common, but it is plausible given the billions of stars in the galaxy and the billions of years that have passed. But if 3I Atlas is on the large end, if it is 5 or 6 kilometers across, you've got a problem. Objects that size are much harder to eject. They're more massive, more gravitationally bound to their home systems. Getting them kicked out into interstellar space requires rare dynamical events, close encounters with multiple planets, stellar flybys, or interactions in binary star systems. It is not impossible, but it is uncommon enough that detecting one in a sample size of 3 interstellar objects would be surprising. It would suggest that either we're incredibly lucky, or that large interstellar objects are more common than our models predict, which would in turn require revising our understanding of planetary system dynamics. This is what statisticians call a black swan problem. The term comes from the philosophical idea that all swans are white until you see a black one, and that single observation overturns your entire framework. 3I Atlas might be a black swan, an object so unusual that its existence forces us to revisit assumptions we thought were solid. Avi Loeb has applied this term to 3I Atlas explicitly, though in his usage he is also tying it to the artificial hypothesis. Loeb's statistical analysis, and I am simplifying here, suggests that given the object's size, trajectory, composition, and lack of non-gravitational acceleration, the probability of it being artificial is somewhere between 30 and 40%. That is his number. It is based on Bayesian reasoning where you assign prior probabilities to different hypotheses and update them based on the observed data. Most astronomers would put that probability much, much lower. They'd argue that Loeb's priors are too generous toward the artificial hypothesis, and that natural explanations, while requiring some special circumstances, are still far more likely. This is a legitimate scientific disagreement about how to interpret ambiguous data, but here is what frustrates me. NASA hasn't engaged publicly with this debate. They haven't explained why they think Loeb's probability estimate is wrong. If they do think it is wrong, they haven't provided their own statistical analysis of how likely it is that 3I Atlas is a natural comet given all the observed properties. They've just stayed silent, which allows Loeb's numbers to circulate without counter-argument. The mass estimate ties directly to the size question. If the nucleus is small, its mass is low and the lack of non-gravitational acceleration becomes very hard to explain. If the nucleus is large, its mass is high and the acceleration puzzle resolves itself through sheer inertia. But we don't know which scenario is correct because we can't measure the size directly. And we can't measure the size directly because we can't resolve the nucleus from the coma. We're stuck in an observational catch-22. There were hopes that the Mars flyby would provide a chance for better size constraints. Spacecraft like ExoMars TGO have higher resolution than ground-based telescopes when observing at close range. But as we discussed, TGO didn't resolve the nucleus either. The viewing geometry, the brightness contrast, and the instrumental limitations all conspired to keep the nucleus hidden, so the size uncertainty persists. What makes this particularly maddening is that the size directly impacts almost every other question we're trying to answer. How much mass is this object losing per orbit? That depends on size. How long has it been active? That depends on how much total mass it started with, which depends on size. Is the lack of non-gravitational acceleration explainable through natural means? That depends on whether the object is large enough to shrug off the jet forces. Could this object survive multiple passes through the inner solar system? Or is this its first and only close approach to the Sun? That depends on its structural integrity, which relates to size. You see the problem. Size is the linchpin variable, and we don't have it. NASA's Hubble team published their size estimate with appropriate caveats. They acknowledge the uncertainty. They explain the limitations of the method. If you read the technical paper, it is all there. But the public-facing communications didn't emphasize how consequential this uncertainty is. They presented it as the nucleus is probably less than a kilometer across, without dwelling on the probably, or on what it would mean if that estimate is wrong. And that is a pattern we keep seeing. Technically accurate statements that omit the context necessary for public understanding. There is another angle to this that is worth considering. If you are NASA and you have data suggesting 3 Atlas might be unusually large, do you lead with that in your press releases, or do you wait until you have confirmation, until you've exhausted every other possibility before making a statement that will generate headlines and speculation? The conservative approach is to say nothing definitive until you are certain. But that conservatism comes at a cost. It creates an information vacuum that gets filled with speculation, rumor, and alternative narratives. And some of those narratives are going to be less tethered to evidence than NASA's cautious silence. I am not saying NASA should be reckless with preliminary data. I am saying there is a middle ground between reckless speculation and opaque silence. And that middle ground is called transparent communication of uncertainty. You can say, our current estimates suggest the nucleus is between this size and that size, and here is why we can't narrow it down further yet. If it is on the small end, it means X. If it is on the large end, it means Y. We're working on getting better data. That kind of statement respects the public's intelligence. It provides context. It acknowledges uncertainty without pretending to have answers you don't have, and it builds trust. But that is not what we're getting with 3i Atlas. What we're getting is silence on the hard questions and carefully worded statements that avoid acknowledging how significant the uncertainties are. And that silence, that avoidance, is why people are starting to ask whether there is something NASA knows that they're not sharing. Maybe there isn't. Maybe the silence is just institutional caution, but the effect is the same. Distrust grows. And in an era where trust in institutions is already fragile, that is a problem NASA should be taking more seriously. Chapter 8, The Pedagogical Exercise Analyzing the Trajectory in September 2025. A paper appeared on Arxiv, the preprint server where researchers post scientific work before formal peer review. The paper was authored by Ian Hibberd, Adam Krah, and Avi Loeb, and it carried a title that immediately raised eyebrows: A Pedagogical Exercise on Close Encounters of the Third Kind. The word pedagogical is key. It signals that the authors are framing their analysis as a teaching tool, a thought experiment designed to illustrate how one might test unconventional hypotheses. But the content of the paper goes much deeper than a classroom exercise. It presents a detailed statistical analysis of 3i Atlas's trajectory and raises questions that, regardless of how you ultimately answer them, are scientifically legitimate. Here is the core argument. 3i Atlas's orbit brings it unusually close to 3 planets in our solar system. It passed Venus at a distance of 0.65 astronomical units, Mars at 0.19 AU, and Jupiter at 0.36 AU. On its own, any one of those close approaches might not mean much. Interstellar objects follow hyperbolic trajectories that intersect the solar system from random directions, and some of those trajectories will inevitably pass near planets by chance. But when you calculate the combined probability of all 3 close approaches happening in sequence, given the object's entry angle, velocity, and orbital plane, the authors arrive at a figure around 0.005%. That is 1 in 20,000. Let me put that in context. If you randomly scattered interstellar objects through the solar system with random trajectories, you'd expect about 1 in 20,000 to pass this close to all 3 planets. That is not astronomically improbable. It is not "this could never happen naturally" territory, but it is uncommon enough that it warrants attention, especially when combined with the other anomalies we've been discussing. The authors of the paper are very careful to state that low probability does not equal impossibility. They acknowledge that unlikely events happen, but they also argue that when you are dealing with an object that already displays multiple unusual characteristics, a statistically improbable trajectory adds to the cumulative case for taking a closer look. Now, here is where it gets really interesting, and where the paper moves from statistical observation to hypothesis testing. The authors note that 3i Atlas's perihelion, its closest approach to the Sun, occurs on October 29, 2025, almost precisely during solar conjunction. Solar conjunction is the period when an object passes behind the Sun from Earth's perspective, making ground-based observation impossible. The Sun's glare drowns out everything in that region of space. If you were designing a trajectory for a spacecraft that wanted to enter the inner solar system unobserved, or that wanted to perform a braking maneuver near the Sun without being easily tracked, perihelion during solar conjunction would be an optimal choice. The paper introduces the concept of a reverse solar Oberth maneuver. An Oberth maneuver is a technique used in spaceflight where you fire your engines at perihelion, the point of closest approach to the Sun, to maximize the efficiency of your propulsion. Because your velocity is highest at perihelion, the same thrust produces a larger change in orbital energy. It is a well-established principle in astrodynamics. A reverse Observatories maneuver would be using thrust at perihelion not to accelerate and escape, but to decelerate and remain bound to the Sun, potentially establishing a long-term orbit. The authors calculate that if 3I Atlas were a spacecraft attempting to break into solar orbit, it would need to shed approximately 44 kilometers per second of velocity. That is a massive delta V, far beyond what any chemical propulsion system could achieve. But if the object has been venting material for months, if its observed outgassing is actually exhaust from a controlled propulsion system using volatiles as reaction mass, the numbers start to become plausible. Not easy, not simple, but within the realm of theoretical possibility for an advanced propulsion system. Let me be absolutely clear about what this paper is and is not claiming. The authors explicitly state that they are presenting a hypothesis to be tested, not a conclusion to be accepted. They say, and I am paraphrasing, if 3I Atlas were an artificial object attempting to enter solar orbit, its trajectory would look approximately like what we observe. This allows us to make testable predictions. If the object performs maneuvers consistent with braking after perihelion, that would support the hypothesis. If it continues on an unbound hyperbolic trajectory with no further anomalies, the hypothesis is falsified. That is how science works. You propose an idea, you derive predictions, you test them against reality. The problem, and this is what drives the controversy, is that even framing the question this way feels taboo. The scientific mainstream has a strong allergic reaction to anything that smells like ufology or ancient astronaut theories, and that reaction is understandable given the mountains of pseudoscience that get peddled under those labels. But it also means that legitimate edge case hypotheses that are statistically unlikely but not impossible, get dismissed without serious engagement. Loeb and his co-authors are trying to thread a needle, proposing an unconventional idea while maintaining scientific rigor, and they're getting pushback, not because their math is wrong, but because the idea itself makes people uncomfortable. NASA hasn't responded to this paper publicly, not with a press release, not with a statement, not with a technical rebuttal. There has been no engagement, and you can argue that is appropriate. NASA doesn't have to respond to every preprint that appears on Arxiv, but this isn't just any preprint. It is an analysis of an object that NASA is actively studying, authored by researchers at major institutions, and it is generating significant media attention. A response would be valuable. It would clarify the agency's position. It would give the public a framework for understanding why mainstream astronomers think this hypothesis is unlikely. But there has been silence. Let's talk about the planetary close approaches in more detail because they're worth understanding. Venus at 0.65 AU means 3I Atlas passed about 97 million kilometers from Venus. That is not particularly close in planetary terms. Venus's gravitational influence on the object would be negligible at that distance. Mars at 0.19 EEEE is closer, about 28 million kilometers. Still not close enough for a significant gravitational interaction, but close enough that spacecraft in Mars orbit had a viewing opportunity, which we discussed earlier. Jupiter at 0.36 OR is about 54 million kilometers. Jupiter's massive, so its gravitational sphere of influence is large, but at that distance, the effect on 3I Atlas's trajectory would be minor. The author's point isn't that these close approaches involved gravitational assists or slingshots. They're not arguing that 3I Atlas used planetary flybys to modify its orbit like spacecraft do. Their point is purely statistical. The trajectory that brings an object near all three of these planets in sequence while also timing perihelion during solar conjunction is uncommon. And if you are looking for patterns that might suggest intentionality, this is the kind of pattern you'd look for. Critics of the paper argue that the authors are cherry-picking. They're taking an object that happened to have an unusual trajectory, calculating the probability after the fact, and then acting surprised that it is low. This is called the Texas sharpshooter fallacy. You fire bullets at a barn, then paint targets around the holes and claim you are a great shot. The counter-argument from the authors is that they're not claiming the low probability alone proves anything. They're saying it is one data point in a larger constellation of anomalies, and that the cumulative weight of multiple anomalies justifies closer scrutiny. Who is right? That is not a question I can answer definitively. What I can tell you is that this is a legitimate scientific debate, and it is being conducted with mathematics, statistics, and testable predictions. That is good. That is how these things should be hashed out. What frustrates me is that the debate is happening almost entirely in academic circles, and on social media with no input from NASA, the institution that has the most data and the most resources to settle the question. NASA could release detailed trajectory analysis. They could publish their own statistical assessment. They could explain what orbital parameters they're tracking and what they'd consider anomalous, but they're not doing that. And in the absence of that engagement, speculation fills the void. The paper makes one more prediction that is worth noting. If 3I Atlas is attempting to break into solar orbit, optimal Earth intercept, meaning the point at which a trajectory bound for Earth would be established, would occur in late November to early December 2025. That is soon. That is testable. If the object continues outbound on its hyperbolic trajectory, if it shows no signs of orbital modification, the hypothesis is dead. If something changes, if the orbit deviates from predictions in ways that suggest braking, then we have a genuine scientific mystery that demands explanation. Either way, we're going to get an answer based on observations, not speculation, and that is good. But here is the thing that keeps me up at night about all of this. What if the answer is ambiguous? What if 3 Atlas does something unexpected, but it is subtle enough that it could be explained either as natural outgassing effects or as controlled propulsion? What if we're left with dueling interpretations of the same data with no clear way to decide between them? That is the scenario that would create maximum public confusion and minimum institutional credibility. And based on NASA's communication strategy so far, I am not confident they're prepared to handle that scenario transparently. Chapter 9. The anatomy of the communication gap. If you go to NASA's official website right now and search for information on 3I Atlas, you'll find a page that lays out the basic facts. It tells you when the object was discovered, what its orbital parameters are, when perihelion occurs, and that it poses no threat to Earth. All of that is accurate. All of that is technically correct. But if you then compare that public-facing summary to the detailed findings published in academic journals, to the spectroscopic data we've been discussing, to the mass ambiguity, the acceleration puzzle, and the statistical trajectory analysis, you start to see a gap, a significant one, the gap between what is true and what is emphasized, the gap between data and context. NASA's statement says 3I Atlas is a comet. Correct. It says it is on a hyperbolic trajectory. Correct. It says it has been observed by multiple telescopes including JWST and Hubble. Correct. What it doesn't say is that the chemical composition doesn't match any known class of solar system comet. It doesn't say that the lack of non-gravitational acceleration, despite substantial outgassing, is unexplained. It doesn't say that the size uncertainty spans more than an order of magnitude, and that the true size has major implications for how we interpret everything else. It doesn't mention the statistical improbability of the trajectory. It doesn't address the speculative hypotheses that are circulating in the scientific community. This is what I mean by the communication gap. NASA isn't lying. They're not fabricating data or hiding evidence, but they're presenting the information in a way that minimizes the strangeness. That makes 3I Atlas sound like just another interstellar comet when the reality is far more complex. And you can argue that this is responsible communication, that you shouldn't alarm the public with speculative ideas or unresolved mysteries. But I'd argue the opposite. Treating the public like they can't handle complexity is condescending and it backfires. People sense when they're being given a sanitized version, and that sensing breeds distrust. Let's look at a specific example. In August 2025, when the JWST spectroscopic data was released, NASA's press release highlighted the detection of carbon dioxide and water, mentioned the unusual ratio, and quoted a scientist saying it was an exciting finding that will help us understand the diversity of comets. That is all true. But compare that to what the actual paper published in the Astrophysical Journal says. The paper notes that the carbon dioxide to water ratio of 8:1 is unprecedented in the observed comet population, and that standard formation models do not predict this composition. The paper discusses the two possible explanations: extreme radiation exposure or unusual formation location, and explicitly states that both require special circumstances. That nuance, that acknowledgement that we're looking at something genuinely anomalous, is absent from the press release. Why? Why would you water down your own findings when you communicate them to the public? The most charitable interpretation is that NASA's public affairs team is trying to avoid sensationalism, trying to prevent headlines that scream, "Alien comet baffles scientists." But in avoiding sensationalism, they're also avoiding transparency. They're making editorial decisions about what the public needs to know versus what scientists discuss among themselves. And those editorial decisions shape public perception in ways that may not align with the actual state of scientific understanding. Then, there is the eye-old situation, and this one is genuinely murky. The International Asteroid Warning Network, ORN, is a framework coordinated by the United Nations for tracking near-Earth objects that could pose impact threats. It is activated when an object is identified that requires enhanced tracking and risk assessment. In September and October 2025, reports circulated in astronomy forums claiming that ORN had been activated for 3I Atlas. Some of these reports cited unnamed sources within European space agencies. Others pointed to increased observation time being allocated to 3I Atlas by various telescopes as evidence of elevated concern. NASA has never confirmed or denied ORN activation for 3I Atlas. There has been no official statement. Now, if ORN was activated, that would be significant because it would indicate that someone, somewhere in the network of space agencies, flagged 3I Atlas as requiring special attention beyond routine scientific observation. It would suggest that trajectory analysts saw something in the orbit that warranted closer monitoring, but without confirmation, we're left with rumors. And rumors are corrosive to trust because they can't be verified or falsified. A simple yes or no from NASA would settle this. The fact that we don't have that answer is by itself a failure of communication. Let's consider why space agencies adopt conservative communication strategies. There are legitimate reasons. Public panic is real. If you release information that is misinterpreted or taken out of context, you can create unnecessary fear. We've seen this with asteroid close approaches that get reported as near misses, when in reality they're millions of kilometers away. Space agencies also have to maintain credibility with the scientific community. If they hype preliminary findings that later turn out to be wrong, they damage their reputation. So there is a balancing act between transparency and responsibility. But here is the problem. That balancing act has tilted too far toward caution with 3I Atlas. The object is not a threat. NASA has said so repeatedly and the orbital data supports that. There is no risk of impact. So the usual justification for withholding information, avoiding panic, doesn't apply. What we're left with is an object that is scientifically fascinating, genuinely unusual, and being communicated about in ways that downplay its significance. And the only explanation I can come up with for that approach is that NASA wants to avoid engaging with the more speculative interpretations. They don't want to give oxygen to the artificial origin hypothesis. They don't want headlines linking NASA's name to anything that sounds like UFOs or alien spacecraft. That is understandable from a PR perspective, but it is short-sighted, because the silence doesn't kill the speculation, it fuels it. When NASA refuses to address Loeb's papers, when they don't explain why mainstream scientists think his probability estimates are too high, when they don't engage with the trajectory analysis or the acceleration puzzle in public forums, they create a narrative vacuum. And that vacuum gets filled by people who are less cautious, less rigorous, and less concerned with evidence. You end up with YouTube videos claiming NASA is covering up alien contact, with social media threads spinning wild theories, and with a public that doesn't know who to trust. NASA could short-circuit all of that with a single comprehensive briefing. Bring together the scientists who are actually working on 3I Atlas. Have them present the data transparently, including the uncertainties and the unresolved questions. Address the speculative hypotheses directly. Explain why most scientists favor natural explanations, but acknowledge that we're still gathering data. Treat the public like intelligent adults who can handle complexity and uncertainty. That kind of transparency would build trust. It would give people a framework for understanding the legitimate science versus the speculation, but we're not getting that. We're getting piecemeal press releases and silence on the hard questions. There is another dimension to this that is worth mentioning, the international aspect. 3I Atlas is being observed by telescopes and spacecraft operated by agencies all over the world. ESA, JAXA, national observatories in Chile, Hawaii, the Canary Islands. This isn't just NASA's story. And yet the public communication is dominated by NASA, or more accurately, by the absence of NASA communication. Other agencies have been even quieter. ESA released basic information about the ExoMars observation, but nothing since. There has been no coordinated international statement, no joint briefing, no unified messaging. That fragmentation makes it harder for the public to get a clear picture. What bothers me most is the missed opportunity. 3I Atlas is a genuine scientific discovery. It is the third confirmed interstellar object we've ever detected, and it is displaying characteristics that challenge our models. This should be a moment of public engagement with science, a chance to show people how the scientific method works when you encounter something unexpected. Instead, it is becoming a case study in how institutional caution creates space for conspiracy thinking. And that is on NASA. They have the platform, the credibility, and the data to control this narrative. They're choosing not to. So, when people ask me, is NASA hiding something about 3I Atlas? I don't think they're hiding data. The data is published. It is in the journals. But they're hiding context. They're hiding the genuine scientific uncertainty and the real debates happening within the research community. They're presenting a confident, simplified narrative to the public while the scientists themselves are scratching their heads about multiple unresolved puzzles. That is not transparency. That is management. And when the public realizes they're being managed, trust evaporates. Chapter 10, Perihelion, The Critical Moment, October 29th, 2025. That is today's date as this video is being released, or perhaps yesterday or tomorrow depending on your time zone. Right now, 3I Atlas is passing through perihelion, its closest approach to the Sun at a distance of roughly 17 million kilometers. That is close. Not as close as some comets get, but close enough that solar heating is at maximum. Outgassing should be at peak intensity. And if this object is going to do anything unusual, this is when we'd expect to see it. And here is the frustrating part. We can't observe it directly from Earth. The object is in solar conjunction, positioned behind the Sun from our perspective. The Sun's glare makes observation impossible for ground-based telescopes. We're flying blind at exactly the moment when the most interesting things might be happening. It is like watching a thriller where the screen goes black during the climax. You know something's happening, but you can't see it. But we're not completely blind. There are two spacecraft that might be positioned to observe 3I Atlas near perihelion, Parker Solar Probe and ESA's Solar Orbiter. Both of these spacecraft are designed to study the Sun from close range, and their orbits take them inside Mercury's orbit, into regions where the Sun's corona can be directly imaged. Parker Solar Probe is humanity's closest approach to the Sun, swinging within a few million kilometers on its elliptical orbit. Solar Orbiter operates farther out, but with instruments that can image the space around the Sun in multiple wavelengths. If 3I Atlas passes through their fields of view, if their instruments happen to be pointed in the right direction, they could capture data that ground telescopes can't. Here is the problem. Neither NASA nor ESA has confirmed that these spacecraft are actively targeting 3I Atlas. There has been no press release saying Parker Solar Probe will observe the interstellar comet during perihelion. There has been no announcement of coordinated observations, which means either the observation isn't happening or it is happening but hasn't been publicly disclosed yet. And given everything we've discussed about NASA's communication approach, either scenario is plausible. If Parker or Solar Orbiter did capture data, we won't see it immediately. Spacecraft data takes time to downlink, to process, to analyze. We might be weeks or months away from any publication. But the fact that we don't even know if the observation was attempted adds another layer of frustration. This is a unique opportunity. 3I Atlas won't be this close to the Sun again. It is leaving the inner solar system on an unbound trajectory. This is our one chance to study it at maximum activity, and the public doesn't know if that chance is being taken. There is one more potential observer, the JWST weather satellite. As I mentioned earlier, JWST is a geostationary satellite positioned over the Western Hemisphere, and its cameras can see beyond Earth. During the solar conjunction period, JWST's viewing angle might allow it to image 3I Atlas while Earth-based telescopes can't. But again, no confirmation, no official statement, just speculation. Chapter 11, The Months Ahead, Observation and Ambiguity Post-Perihelion Visibility is more certain. Starting in early November 2025, 3I Atlas will emerge from behind the Sun and become visible in the morning sky before sunrise. By mid-November, it will be moving through the constellation Virgo, still bright enough to be observed by amateur astronomers with decent equipment, magnitude 10 or brighter. Through December, it will continue outbound, passing through Leo, gradually fading as it moves away from both the Sun and Earth. By early 2026, it will drop below magnitude 12, which puts it out of reach for most amateur telescopes. Professional observatories will continue tracking it for as long as possible, but eventually it will fade into the distance and disappear. This post-perihelion period is when we'll get answers to some of the questions we've been discussing. If the object's orbit deviates from gravitational predictions, if there is any sign of trajectory modification consistent with braking, it will show up in the astrometry data collected during November and December. This is where the hypothesis from the ArXiv paper becomes testable. The authors predicted that if 3I Atlas were attempting to establish an Earth intercept trajectory, optimal positioning would occur in late November to early December. That is a specific prediction with a specific time frame. we're going to get an answer. I want to be very clear about something. There is no credible threat, no space agency, no astronomer. No one in the mainstream scientific community has suggested that 3I Atlas poses any danger to Earth. Its closest approach to our planet occurred back in July 2025, at a distance of over 120 million kilometers. That is nearly the distance from Earth to the Sunday. It is not coming back, even if its orbit were modified. Even if it somehow became bound to the solar system, the trajectory would not intersect Earth. So when I talk about Earth intercept in the context of the ArXiv paper, I am referring to a theoretical scenario explored in a thought experiment, not an actual predicted event. But here is where things could get interesting. If 3I Atlas does deviate from its predicted trajectory, even slightly, it will create a scientific firestorm. Mainstream astronomers will scramble to explain it through natural means, maybe a sudden outburst from a collapsing subsurface cavity, maybe a fragment breakup that altered the mass distribution, maybe something we haven't thought of. Loeb and others will point to it as evidence supporting the artificial hypothesis. The media will go wild and NASA will be forced to make a statement. That is the scenario I am watching for. Not because I think 3I Atlas is a spacecraft. I genuinely don't know what it is and I am comfortable with that uncertainty. But because the response to an anomalous trajectory deviation will reveal a lot about how space agencies handle discoveries that don't fit the standard narrative. Will they be transparent? Will they release the data immediately and let the scientific community debate openly? Or will there be delay, careful messaging, and managed disclosure? There is also the question of the Europa Clipper and Hera spacecraft. Both of these missions were launched in 2024, and trajectory analysis suggests their paths might intersect 3I Atlas's coma or tail during November and December 2025. If that happens, the spacecraft's instruments could sample the gas and dust environment directly. That would be an incredible scientific opportunity. Direct sampling of interstellar material is something we've never done before. The particles and molecules that make up 3I Atlas's coma originated in another star system. They carry information about that system's chemistry, its formation history, its stellar environment. Getting that data would be a goldmine, but once again, no confirmation from NASA or ESA about whether these spacecraft are being tasked for observations. We're left speculating about opportunities that might be happening or might be missed, and that uncertainty is exhausting. It feels like we're constantly one step behind the information we need to understand what is actually going on. The timeline for the next few months is clear. November through January will be the critical observation window. Observatories around the world will be tracking 3I Atlas, measuring its position with precision, looking for any deviations from the predicted orbit. Spectroscopic observations will continue to monitor gas production rates, composition changes, and activity levels. All of that data will be published eventually, though eventually in astronomy can mean months or years. And then sometime in 2026, 3I Atlas will fade beyond observational reach. It will join Oumuamua and Borisov in the small list of interstellar objects we've detected and studied, and we'll be left with whatever data we manage to collect, trying to piece together a coherent explanation for all the anomalies. The question that keeps echoing in my mind is, will we get a clear answer? Or will 3I Atlas remain ambiguous, an object with too many unusual features to be dismissed as ordinary, but not quite strange enough to force a paradigm shift? Because that is the outcome that would be most challenging. Ambiguity is hard for humans to tolerate. We want closure. We want to know whether this is just a weird comet or something more. But science doesn't always provide clean answers, especially when you are dealing with objects billions of kilometers away that you can only study through the light they reflect or emit. Sometimes the answer is, we don't know and we might never know for certain. And if that is where we end up with 3I Atlas, the question becomes, how do space agencies communicate that uncertainty without losing public trust? Based on what we've seen so far, I am not optimistic. Conclusion, the bigger picture and the demand for transparency. Let's step back from 3I Atlas for a moment and talk about the bigger picture, because this isn't really a story about one object. It is a story about how scientific discoveries are communicated to the public, about who gets to decide what information is important, and about the gap between institutional caution and public trust. 3I Atlas is just the catalyst, the specific case that makes these broader issues visible. Here is the truth. We're living in an era where interstellar objects are going to become more common, not because there are more of them, but because our detection capabilities are improving. The Vera C. Rubin Observatory, which is set to begin operations soon, will revolutionize sky surveys. It will detect faint, fast, moving objects that previous telescopes would have missed entirely. We found 3 interstellar objects in 8 years, Oumuamua in 2017, Borisov in 2019, and 3i Atlas in 2024. With Rubin online, we might find dozens per year, maybe hundreds. That means the communication challenges we're seeing with 3i Atlas are going to repeat over and over. Each new interstellar visitor will raise questions. Some will be straightforward, easily explained by standard comet models, but some, statistically, will be weird. They'll have unusual compositions, strange trajectories, unexpected behaviors. And each time that happens, space agencies will face the same choice: be transparent about the uncertainty and the scientific debate, or manage the message to avoid speculation. What I am arguing, what I hope is clear from everything we've discussed, is that the management approach doesn't work. It backfires. It creates distrust. It makes people feel like they're being kept in the dark, like there is a two-tier system where scientists get the real story and the public gets a simplified version. And in an era where trust in institutions is already fragile, where misinformation spreads faster than corrections, that approach is corrosive. So what should NASA do differently? What should we, as the public, demand? First, transparency about uncertainty. When you don't know something, say so. When the data is ambiguous, explain why. When there are competing hypotheses within the scientific community, present them fairly instead of pretending there is consensus when there isn't. People can handle uncertainty. What they can't handle is the feeling that they're being fed a sanitized narrative. Second, engage with speculative ideas openly. When researchers like Avi Loeb publish hypotheses about artificial origins, don't ignore them. Explain why most scientists disagree. Show your work. Present the statistical reasoning, the evidence, the alternative explanations. Make it a teaching moment instead of a taboo topic, because silence doesn't kill speculation, it amplifies it. Third, real-time data access. We have the technology to make observational data available to the public as it is collected. Not raw, uncalibrated data that requires expertise to interpret, but processed data with context and explanation. When JWST observed 3i Atlas in August 2025, there is no reason the spectroscopic data couldn't have been released immediately with a briefing explaining what it shows. Yes, peer review takes time, and that is valuable. But preliminary findings can be shared while the formal publication process is ongoing. Other fields do this. Astronomy can too. Fourth, international coordination. 3i Atlas is being studied by agencies and observatories around the world. There should be a coordinated communication strategy. A single authoritative source where people can get updated information, instead of piecemeal press releases from different agencies at different times. Coordinate. Present a unified picture. Make it clear that the global scientific community is working together and sharing information freely. And finally, respect the public's intelligence. Stop assuming people can't handle complex ideas or ambiguous data. The audience for this kind of content, the people who seek out information about interstellar objects, are not casual observers. They're engaged, curious, often highly educated. They can understand nuance. They can follow statistical arguments. They can tolerate uncertainty. What they can't tolerate is being patronized. Here is why this matters beyond just 3i Atlas. We're on the edge of a new era in astronomy. JWST is operational. Rubin is coming online. The next generation of extremely large telescopes is under construction. We're going to be making discoveries at a pace that previous generations couldn't imagine. Some of those discoveries will be strange. Some will challenge existing models. Some will be ambiguous enough that they generate legitimate scientific debate. If the communication strategy for each of those discoveries is to downplay the strangeness, to wait months or years before releasing contextual information, to avoid engaging with speculative interpretations, we're going to have a problem. A big one, because the alternative to institutional transparency isn't ignorance. It is alternative information sources. It is YouTube channels and social media threads and forums where people piece together fragments of information and fill the gaps with speculation. Some of that speculation will be responsible and evidence-based. A lot of it won't be, and the public will be left trying to navigate between institutional opacity and speculative noise with no clear way to distinguish credible analysis from nonsense. 3i Atlas has given us a preview of that future. Look at what has happened over the past year. NASA released data, but without adequate context. Researchers published papers raising unconventional hypotheses. Social media exploded with speculation, some informed, some wild. Unverified claims about observations circulated without confirmation or denial, and the public was left confused, uncertain who to trust. Frustrated by the lack of clear information, That is a failure. Not a failure of science, but a failure of communication. So, here is what I am asking you to do. Don't just passively consume the information that space agencies decide to share. Demand more. Demand transparency. Demand engagement with the hard questions. Demand real-time access to data and clear explanations of what it means. And when you see gaps between what is published in academic journals and what is communicated publicly, call it out. Write to NASA. Write to your representatives. Make it clear that you expect better, because this isn't just about satisfying curiosity. It is about maintaining the social contract between scientific institutions and the public that funds them. Your tax dollars pay for these missions, these telescopes, these observations. You have a right to understand what is being discovered, not a year later, not filtered through press releases written by PR professionals, but in real time with the context necessary to make sense of it. 3 Atlas is still out there right now, passing behind the sun. We don't know yet what the next few months will bring. Maybe the orbit will be exactly as predicted, confirming it is a natural interstellar comet with unusual but ultimately explainable properties. Maybe there will be deviations that deepen the mystery. Either way, we're going to learn something. The question is whether that learning will happen transparently with the public as active participants, or whether it will happen behind the scenes with carefully managed disclosures weeks or months later. I know which future I want. I want a future where space agencies treat the public as partners in discovery, where uncertainty is acknowledged rather than hidden, where the scientific process is visible in all its messy, exciting complexity. I want a future where my kids can follow along with discoveries as they happen, where they can see how scientists debate and test ideas, where they learn that science isn't a collection of facts handed down from authorities, but a process of questioning and evidence and revision. 3 Atlas can be a step toward that future, or it can be another missed opportunity. That choice is in the hands of NASA, ESA, and the other agencies studying this object. But it is also in our hands because they respond to what we demand. If we accept opacity, that is what we'll get. If we demand transparency, if we make it clear that the old model of managed communication doesn't work anymore, they'll adapt. So stay informed. Follow the scientific literature, not just the press releases. Question what is emphasized and what is omitted. And keep asking, why isn't this being explained more clearly? What aren't we being told? Not because there is necessarily a conspiracy, but because asking those questions pushes institutions toward greater transparency. 3 Atlas is a visitor from another star, carrying with it the chemistry of another world, the history of another system. It is a gift of data, a natural probe that came to us from the void. Let's not waste it by allowing it to disappear into institutional opacity. Let's demand the transparency necessary to understand what it really is, even if that answer is, we're not sure, and here is why. That honest uncertainty is worth more than a confident lie, and right now, with everything we've discussed, with all the gaps between data and communication, we're closer to the lie than the truth. If you made it this far, thank you. Drop a comment telling me what you think. Do you trust NASA's communication on 3I Atlas, or do you think there is more to the story? And hit subscribe, because over the next few months, we're going to be following this object's post-perihelion trajectory, and you are going to want to see what happens next.